Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This lesson is part one in a series of 3 videos on vector functions. It is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the video Introduction to Vectors prior to watching this video. In this video, we will discuss the definition of a vector function, continuity, the limit of a vector function, the derivative of a vector function, the tangent vector to a curve, and derivative rules. A vector-valued function of a real variable, more simply called a vector function, r equals r of t, is a function whose domain is a subset of real numbers and whose range is a set of vectors. For a vector function on a plane whose domain is on the interval a is less than or equal to t is less than or equal to b, the components of R are the two real functions x equals x of t and y equals y of t, each defined on the interval a is less than or equal to t is less than or equal to b. R is equal to the vector r of t is equal to the vector x of t y of t is equal to the vector x of t I plus y of t j. For a vector function in space whose domain is on the interval a is less than or equal to t is less than or equal to b, the components of R are the 3 real functions x equals x of t, y equals y of t, and z equals z of t, each defined on the interval a is less than or equal to t is less than or equal to b. R is equal to the vector function r of t is equal to the vector x of t, y of t, z of t is equal to the vector x of ti plus y of tj plus z of tk. A vector function r equals r of t is continuous at a real number t sub 0 if r of t sub 0 is defined, the limit as t approaches t sub 0 of r of t exists, and the limit as t approaches t sub 0 of r of t equals r of t sub 0. For a vector function, r of t equals x of ti plus y of tj in a plane, the limit as t approaches t sub 0 of r sub t equals the limit as t approaches t sub 0 of x of t times I plus the limit as t approaches t sub 0 of y sub t times j, provided the limit as t approaches t sub 0 of x of t and the limit as t approaches t sub 0 of y sub t exists. For a vector function r of t equals x of ti plus y of tj plus z of tk in space, the limit as t approaches t sub 0 of r sub t equals the limit as t approaches t sub 0 of x of t times I plus the limit as t approaches t sub 0 of y sub tj plus the limit as t approaches t sub 0 of z sub tk, provided the limit as t approaches t sub 0 of x of t, the limit as t approaches t sub 0 of y of t, and the limit as t approaches t sub 0 of z of t exists. For example, find the limit of the following vector function. The limit as t approaches pi over 4 of sine ti minus cosine tj. This can be solved with simple substitution. Sine of pi over 4 equals the square root of 2 over 2, and cosine pi over 4 equals the square root of 2 over 2. So the limit equals the square root of 2 over 2i minus the square root of 2 over 2j. In another example, find the limit as t approaches 0 of e to the ti plus secant squared tj plus sine t plus t all over t times k. We can split this at the plus sign to get the limit as t approaches 0 of e to the ti plus the limit as t approaches 0 of secant squared tj plus the limit as t approaches 0 of sine t plus t all over t times k. The limit as t approaches 0 of e to the t equals 1. The limit as t approaches 0 of secant squared t equals 1. The limit as t approaches 0 of sine t plus t all over t equals 0 plus 0 over 0, or the indeterminate form 0 over 0. We can therefore solve this using L'Hopital's rule. ddt of sine of t plus t equals cosine t plus 1. ddt of t equals 1. According to L'Hopital's rule, the limit as t approaches 0 of sine t plus t over t equals the limit as t approaches 0 of cosine t plus 1 over 1, which equals 1 plus 1 over 1, or 2. Therefore, the original limit equals I plus j plus 2k. The derivative of a vector function r equals r of t, denoted by r prime of t equals dr dt, is r prime of t equals dr dt equals the limit as h approaches 0 of r of t plus h minus r of t over h. If r of t equals x of ti plus y of tj, and if x of t and y of t are both differentiable real functions, then r prime of t equals x prime of ti plus y prime of tj, or dr dt equals dx dti plus dy dtj. If the vector function r of t equals x of ti plus y of tj plus z of tk, and if x of t, y of t, and z of t are all differentiable real functions, then r prime of t equals x prime of ti plus y prime of tj plus z prime of tk, or dr dt equals dx of ti, dy dtj, dz dtk. For example, find the derivative of the following vector functions. R of t equals 4 times the square root of ti plus 2 times e to the tj. The first derivative, r prime of t, equals 2 over the square root of ti plus 2 times e to the tj. The second derivative of r of t equals negative 1 over the square root of t cubed I plus 2 times e to the tj. In a second example, r of t equals sine 2ti minus cosine 2tj. The first derivative, r prime of t, equals 2 cosine 2ti plus 2 sine 2tj. The second derivative is negative 4 sine 2ti plus 4 cosine 2tj. Suppose r equals r of t is a vector function defined on the interval ab and differentiable on the interval ab. Let p sub 0 be a point on the curve C traced out by r equals r of t, corresponding to t equals t sub 0, for a is less than or equal to t sub 0 is less than or equal to b. If r prime of t is not equal to 0, then the vector r prime of t sub 0 is a tangent vector to the curve at t sub 0. The line containing p sub 0 in the direction of r prime of t sub 0 is the tangent line to the curve traced out by r equals r of t at t sub 0. For example, find the tangent vector to each curve at t. R of t equals the quantity of 1 minus 3t times I plus 2tj minus the quantity of 5 plus t times k at t equals 0. R prime of t equals negative 3i plus 2j minus k. Therefore, r prime of 0 equals negative 3i plus 2j minus k. R of t equals cosine 2ti plus sine 2tj minus 5k at t equals pi over 4. R prime of t equals negative 2 sine 2ti plus 2 cosine 2tj. R prime of pi over 4 equals negative 2 sine pi over 2 I plus 2 cosine pi over 2j. Sine pi over 2 equals 1 and cosine pi over 2 equals 0. Therefore, r prime of pi over 4 equals negative 2i. The following derivative rules apply to vector functions. ddt of the sum of the vectors v of t and w of t equals ddt of v of t plus ddt of w of t. ddt of f of t times the vector function v of t equals ddt of f of t times v of t plus f of t times ddt of v of t. ddt of the dot product of the two vectors v of t and w of t equals the dot product of ddt of v of t and w of t, plus the dot product of v of t and ddt of w of t. ddt of the cross product of the two vector functions v of t and w of t equals the cross product of ddt of v of t and w of t plus the cross product of v of t and ddt of w of t. ddt of the composite vector function v of f of t equals ddt of v of f of t times ddt of f of t. For example, find ddt of the dot product of v of t and w of t when v of t equals t squared I minus tj and w of t equals ti plus t squared j. ddt of v of t equals 2ti minus j and ddt of w of t equals I plus 2tj. We start with the definition of this derivative from before and fill in the appropriate terms. The dot product of 2ti minus j and ti plus t squared j plus the dot product of t squared I minus tj and I plus 2tj. Simplify to get 2t times t plus negative 1 times t squared plus t squared times 1 plus negative t times 2t. Simplify again to get 2t squared minus t squared plus t squared minus 2t squared. This equals 0. As another example, find the derivative of the cross product of the vector functions v of t and w of t, where v of t equals 2ti plus t squared j minus 5k, and w of t equals t squared I plus 2tj plus k. We start with the definition of the derivative of a cross product. ddt of v of t equals 2i plus 2tj, and ddt of w of t equals 2ti plus 2j. Next, we take the cross product of ddt of v of t times w of t. For this, we use the 3x3 determinant, filling in the first row ijk, and the second row from ddt of v of t, 2, 2t, and 0. Finally, the third row from w of t, t squared, 2t, and 1. This equals the three 2x2 determinants, 2t, 0, 2t, 1 times I, minus 2, 0, t squared, and 1 times j, plus 2, 2t, t squared, and 2t times k. This equals 2ti minus 2j plus the quantity of 4t minus 2t cubed times k. Next, we take the cross product of v of t times ddt of w of t. Again, we use a 3x3 determinant with the first row as ijk, the second row from v of t, 2t, t squared, and negative 5, and the third row from ddt of w of t, 2t, 2, and 0. We solve this using the three 2x2 determinants, starting with t squared, negative 5, 2, 0 times I, minus 2t, negative 5, 2t, 0 times j, plus 2t, t squared, 2t, and 2 times k. This equals 10i minus 10tj plus the quantity of 4t minus 2t cubed times k. We then take the sum of these two cross products to arrive at the final answer, the quantity of 2t plus 10 times I, minus the quantity of 10t plus 2 times j, plus the quantity of 8t minus 4t cubed times k. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.